Hey everyone, Kyle here. It's January 9th, 2025. We're not even 10 days into 2025, but I wanted to make a video that is a bit more of a reflection and maybe kind of like an open-ended video essay of things that have been floating around in my brain over the past couple of months. I made a video kind of like this after the O1 model or O1 preview model came out in November, and I kind of want to do this thing where perhaps once a month I kind of just sit down and I will just dump a lot of thoughts that I've been having into video form and just share that with you all, because I don't see any harm in doing it. I mean, there's not going to be any AI testing, so if anything, it's just going to be a video of me going blah, blah, blah into the camera, and you guys can just tune out. But 2025 is not just momentous because of AI, which I do think that this year is going to be a very pivotal year in human history, because I think the agents are going to start appearing and replacing certain jobs. I mean, Salesforce has, I think, announced that they're not going to hire any more software engineers because of AI agents. So that's a big thing. But not only is 2025 big because of AI, it's big for me personally because I'm turning 30 years old, and I turned 25 right in the middle, or not in the middle, right at the beginning of the COVID-19 pandemic. And so my 20s were evenly split between pre-COVID and post-COVID. And I think when you're going through school, like I was in my 20s, like university and graduate school, getting a PhD in physics, I really never had time to sit down and just think about things and think about the world and my life and topics that were important to me. I was always just so focused on black holes. And it's funny I say it because I also have a book about black holes right here. It's this beautiful book, The Warped Side of Our Universe, An Odyssey Through Black Holes, Wormholes, Time Travel, and Gravitational Waves by Kip Thorne and Leah Halloran. Really beautiful book that combines art and science and poetry. And I know that's a tangent, but it's just a really beautiful book. And I still really do like black holes and physics, if you can't tell. But back to what I wanted to say, the point of all this reflection is that when you're in those settings, university and grad school, you never have time to really think about the present. I think for me personally, I always was concerned about the future, and I never had time to actually sit down and appreciate what I was doing. Maybe not entirely. Of course, I think there were times where I really felt like I was in the moment doing something, but I do think when you're in these terminal places, these places where you know you're not going to spend a certain amount of time beyond in, you don't get to really appreciate so much the present, because you, at the back of your mind, there is always what comes next. And I think AI sometimes puts me in that space too, where I can't even just appreciate what's going on right now. It's always what comes next. And those timelines, those timescales where this question comes up seems to happen every couple of weeks or month now. And who knows, maybe the rate will accelerate. I don't honestly know. I'm just a guy who likes to test AI models on YouTube. I'm not an AI researcher in the traditional sense, but I wanted to share with you some research questions that I've had and I've developed over the years, either through my PhD or through my work here at NASA Ames Research Center. By here, it's over there. I live only like 5 minutes away, which is kind of nice. Or just in my spare time. And I made a list of these questions on my personal website, kylekabasaris.com. I do blog every now and then, some random thoughts of mine, or maybe I'll write a long form thing here and there. So if you want to be more up to date with my inner machinations of the brain, go onto that website. But I wanted to share these ideas because I'm not really afraid of my ideas being scooped or taken, because honestly, it would just thrill me if someone, it doesn't have to be me, could solve these questions. And I think that's the fun part about science, is that when you have shown that you can solve a difficult research problem, like when I went through my PhD, your mind just kind of goes to these places where like, great, like what else can I do, or what else can we do? And then you have to prioritize what are the questions you are really going to actively work on, because unfortunately, as just a human, you don't have the ability to parallelize your tasks as efficiently as like a computer or an ML model. But who knows, maybe all that will change with AI. Like I'm thinking to myself, what if O3 gets released, or O4 or whatever, and we can solve 2 or 3 of these problems in the next 2 years? That would be incredible. But nevertheless, I'm not really motivated by me being the person solving these problems and wanting to hide it from everyone else. I really think that science should be more open sourced and more, less gatekeepy. And I think that really has to do with like the incentive structures too of the system in academia. But since I'm not in academia, I don't really care about sharing these ideas and getting, scooped and my H-index not going up. It doesn't matter to me. So let's begin. What are some of the main questions that I'm hoping AI can help me with? Well, the first two have to do with my job. So at NASA Ames, I'm working on two main kinds of projects. One of them involves LiDAR. So I went to Washington, D.C. last month to give a presentation on the work I was doing with the LiDAR. LiDAR is light detection and ranging. Basically, it's a laser that scans the terrain, and you can get these really nice high-density point clouds. They're on autonomous driving cars, and they are a sensor of sorts. Now, the main question I have with LiDAR, and who knows, maybe people are already actively doing this, and I haven't just found them out yet, but my main question with LiDAR is that can we build some sort of deep learning algorithm that we can get point-by-point semantic segmentation, as in classify each point as part of a tree or a building or the ground or whatever, right? And this is an important question because I work with a lot of airborne LiDAR data that's taken on planes that are meant to scan the Earth's surface to understand topographic changes, wildfire risk mitigation, urban planning, forestry management. And a lot of the data that we have is not well classified at all. And so that really limits the usefulness of the data. If we can get really good, high quality classification that we can do at scale, as in do this on LiDAR data sets that cover the whole United States, for example, which is the data set that I'm working with. It's from the United States Geological Survey. It would just help so many different disciplines. And it's actually one of the problems that I'm hoping to tackle at work over the next couple of months to the next year, at least one of the projects, because I do see it as a really big bottleneck in terms of delaying the usefulness of some of these products that I'm working on creating. So I've created these data products that was part of the Washington, D.C. presentation based on the LiDAR data. And while they are useful, they are limited in their usefulness because of the fact that the raw points themselves are not well classified. So that's what holds them back. I'd love to develop some sort of algorithm, some AI algorithm to classify things and do it very efficiently. That would be a big hope. So that's question number one. Question number two involves geostationary satellites and clouds. So clouds, there are actually no clouds that I can see right now above me, but clouds get in the way of geostationary and low Earth orbiting satellites. And when we want to study the Earth's surface as Earth system scientists, we often need cloud-free images to make inferences on the terrain below, because obviously if there are clouds in the way, they intercept the sun's radiation from above. They also intercept radiation coming from the Earth's surface. And so they mask a lot of the interesting signs that we hope to see. And so I have been working on, over the past year, in addition to the LiDAR stuff, working on cloud detection algorithms. And now there are many cloud detection algorithms out there. They've been around since the 1980s even. A lot of them are based on traditional physical theories like radiative transfer. So that's just the study of electromagnetic radiation interacting with matter. And the AI models that I've seen that don't use radiative transfer can often get a better cloud mask, as in better identification of which pixels in a satellite image on the pixel by pixel scale. What are clouds? What are not clouds? What are shadows? What are just clear pixels? The thing is, though, is that cloud detection algorithms are notoriously finicky in the sense that you can train an algorithm on a satellite, let's say Sentinel-2 or GOES or MODIS, Landsat, all these different satellites that are orbiting the Earth. And the issue is that you can train it over one of these satellites over a specific region of Earth for maybe a specific time of day, for a specific time of year, and it might do well in this very, very limited context, but we want a general purpose AI algorithm, maybe not even just AI, but a general purpose algorithm that no matter what angle the sun is at in the sky, no matter what time of day it is, or what time of year it is, or what geographic location you are, it can reliably classify clouds not clouds, cloud shadows, and the sorts. And now, of course, this gets into very tricky questions because clouds are not just one thing. You have cirrus, you have cumulonimbus, you have stratus. You have so many different types of clouds, different properties. Some that are thin, some that are thick and very opaque. And then you have to, of course, decide some threshold. And that's always the issue, right? What's the threshold? What is that threshold that we should pick? And the physics that governs clouds go all the way from microphysics on the scales of little cloud droplets all the way up to kilometer, mile wide scales. And so it's such a challenging problem, but I think it's frustrating too, because we can see the pieces of what a good solution would look like, but it's sort of getting them all to work together all around in terms of time of day, sun angle orientation, when, if the sun is not just directly overhead, but it's sort of, off zenith, and you're getting shadows and glint and scattering effects. It's just all these different edge cases that really throw off a general purpose algorithm. So anyways, that is another question that I've been having and have been working on. There's a lot of papers on it, but again, we want something that is robust in multiple different settings. And so far, the best I've been able to do is just do it over like one or two different kinds of land cover over with one specific satellite, as opposed to a general purpose algorithm on multiple satellites. But it'll be hard because satellites have different properties. They have different light sensor properties. They have different digital image resolutions, and that also complicates things. So anyways, I know I've been blabbing a lot about this, but it's a question that I hope that we can solve and help us understand the Earth system better. Because let's move on to question number 3 now. Question number 3 is something that I've thought about a lot since I was a child, because it has to deal with the connection between artificial intelligence and autism in humans. And my younger brother, Chad, is an individual who has autism, and he's unable to talk, so he doesn't know how to form words. And it's hard at times to really understand what he wants and what he needs. But he does have behavioral cues and patterns that we as his family have been able to learn over the years, and just intuitively know what he needs or wants, or at least have some semblance of an idea of what he needs or wants. And I've always thought about some sort of device or some sort of technology that can help improve that flow of communication, and also identify when perhaps he's not physiologically in equilibrium, right? Because there have been times in life where Chad has had some health problem that we don't know about, because he just can't vocalize what is going on with him, and then he has some emergency. And so I think that having some sort of AI technology that can somehow better interpret behavioral patterns, using histories of patient medications or doctor's reports, behavioral reports, things of that nature, to get better at responding to what a person with autism needs in that moment in time, and perhaps even reading physiological state and health and condition and things of that nature. I know it sounds kind of far-fetched, but with artificial intelligence and all the technology that's been coming out over the past couple of years, perhaps this isn't far-fetched. Perhaps it's something that we could realize in the next 5 to 10 years, maybe sooner. I don't know. Maybe longer. I don't even understand really how FDA approval works and how these technologies get screened and approved. So anyways, that's a very personal research question that I have, and have made some efforts in that direction. There's a blog post about this RAG, Retrieval Augmented Generation AI model, that I've been working on my website, which you can read about it in the description below, and I'll put a post or a picture of it right here. So that's that. I would say question number 4 is a question I've had since I was in graduate school, and this ties in with what I was doing as a graduate student, which was, studying supermassive black holes, kind of like topics in these pictures here, but less artistic. But one idea I've been having lately that I never got around to in graduate school is that, could we actually make good enough synthetic data to train AI algorithms to measure the masses of supermassive black holes. What I mean by that is that when I was in grad school, what I would do is that I would measure these black hole masses, as in we would have a data set of the dynamics of some system. So it was typically, or it was always, a rotating disk around the supermassive black hole that we can model with Newton's laws and get an estimate of what the black hole mass should be to reproduce those dynamics, right? So it's like you have the gas, you can measure its velocity, it's moving in this very nicely rotating disk, and you can use physics to infer, okay, what's the mass of the thing in the very center, what it should be, what we presume the black hole's mass should be. And I remember thinking to myself, wow, we have such limited data sets of this quality, because the telescope I was using, the Atacama Large Millimeter Array, has only been around for 10 years, and not everyone tries to measure black hole masses in astronomy, even though they should. And so that made me wonder, is it possible if we could create just really good synthetic data that's governed by really good physics? As in, we know what some analytic profiles of what mass distributions, like what kind of velocity curve of the particles in an object's gravitational well, what they should look like. So for example, we know, very massive spheres. We kind of know the physics of very massive spheres. And if you have a, test particle at a certain radius from a very massive sphere, you know roughly what its velocity profile should look like. And I was just wondering, could we just make some sort of really good synthetic data set of these analytic models that we sprinkle in some observational properties that we've seen, and or just things you would expect after observing the data through a telescope, really recreating the optical imagery that we see, or technically it's radio and millimeter wave imagery we see at the end. But if that makes any sense, like, can we just use synthetically created, physically relevant and accurate models to train AI models to make black hole mass predictions? I have no idea. It's a cool idea, but I wish I had time to work on it. But again, this video is about all the ideas that I'm either working on right now, like at work, or wish I could be working on right now. And if you have time to work on these ideas, I'd love to talk to you, because it would be great to have people work on some of these ideas. So that's question number 4. And finally, question number 5 is a more fundamental question, but it really gets at the heart of what makes deep learning so effective. We really don't know why deep learning works as well as it does. We know that it works because it's able to make these predictions, and we have these chatbots, and we have these reasoning models, and so we know that deep learning works, but fundamentally we don't really know why. And that's just kind of unsatisfactory to me, to know that something works, but not know how it works or why it works. Because I just feel as if you're ignorant of the weaknesses, of the areas where it can go wrong, or it's nice to have some sort of fundamental understanding of something. And I'm saying that as a physicist, right? So that would be nice, but perhaps any biologist could tell me, like, Kyle, what do you know? What do you mean about fundamental understanding? Like, complexity is everywhere. And I think that's where physics gets people like me in trouble, where we have such a very reductionist view of the world. Our mental models are very simplified. And so when we're introduced to complexity, it just muddies the waters. And so I'd really love to know how deep learning ticks, right? And not just imagine it as just these large floating point matrices that are working in 12,000 dimensional space. I'd like to have a better understanding. Okay, so with all of my research questions out of the way, I suppose it's time for me to maybe end with some speculation of how I think this year might go, even though I could be wildly wrong, and I'm totally open to being wildly wrong, but I just think it would be kind of fun to make a speculation. And plus, I kind of want to make videos like this, like maybe every month or so, where I kind of give you my latest updates on how I think about things and where things are with my own research progress. And I just want to keep learning, and I just want to keep my eyes and ears open to the next latest developments in AI. So where do I think things are going? I think AI agents are going to be a thing this year. Salesforce, I believe, has just announced that they're not going to hire any more software engineers in 2025. If I'm not mistaken, I know there are some people on YouTube who are saying that they've started whole new companies just using AI themselves, getting rid of human labor. I do think that we're going to start seeing the impacts of AI on the job market this year, if not already. People already say it's been happening since 2023, 24, but I still think that I'm living in kind of a bubble here in Northern California, that I'm just so close to the action that it feels like everything's happening so fast, but really the ripple effect hasn't reached people, not in the bubble. And that's another question. Is this just a bubble? Is this just a huge waste of time and resources and money from these companies, and are investors being duped? I don't think they're being necessarily duped, but I do think that the relationship between investors, VCs, and the companies is having an effect on the rate at which things are progressing, as well as the conversations around safety and alignment. I do think that it's fascinating to see, as an outsider who's not an active AI researcher, how market forces and technology and companies and people get all tangled with each other. And coming from academia, right, where you have zero experience with that, pretty much, it's something to behold. I'm not going to comment as to whether I think it's good or not. It's just different from what I'm used to, and I think I need to wait and see how this plays out. So yeah, that's kind of my prediction for this year. We're going to see a lot of AI agents and robots, maybe. I don't know. It's hard to tell these days. Like I see these clips of robots in China, and I have a hard time distinguishing whether it's real or not real. So perhaps even robots are coming for more manual type of jobs. So anyways, with that, I think I'll conclude my ramblings and my thoughts. I appreciate it if you made it this far. It's fun to share ideas and think of a more beautiful future, a more safer and healthier and cleaner planet that I'd love to see and realize one day. But we're not there yet, and I think there are a lot of challenges that need to get solved first. So thanks for watching. I'll be back with more videos in the future, and I wish you all a great day.